The topic of our first 2008X module is machining, which I think is appropriate given the history and significance of machining to manufacturing, and also the fact that machining can be used on so many different materials and achieve so many different geometries. Now we're assuming that you've studied machining a little bit before, or you've used a mill or a lathe, the two most common machine tools. And if you used a mill, you might have seen a picture like this or watched this process in action, which is the removal of material from the side of a piece of metal. And as we'll learn, machining is a lot about the mechanics of interaction between the tool, here the cutter that rotates, and the material which is removed. And one of the things we do with machining in our MIT manufacturing class is machine injection mold tooling. And this is two blocks of aluminum that have been machined both by milling and turning, and they're used as molds to make pieces of yo-yos, which are our class project. Machining has been around for a long time, of course. Here's a picture of a machine shop in the DC printing office in 1909. And here you see machinists using lathes to execute the turning process. And over at the right is a picture of a more modern machine shop with computer numerically controlled or CNC machine tools. And arguably the mechanics of machining are the same, although the process has advanced a lot in that time. And nowadays, being successful at machining also involves choosing the right tool, and there are many different kinds of tools with different materials and coatings and different shapes, and choice of those tools is important to be able to make the right kinds of features with the right kinds of quality. Here's a question for you. What do you think is the highest volume machined part in history, or CNC machined part in history? And by highest volume, I mean the single part that's been made in the largest quantity. You might have a different answer, but I think it is the iPhone 6, or the housing of the iPhone 6. Apple reported that in 2015 it sold over 150 million iPhone 6s, and the housing of each phone is identical, at least in terms of its structure. So here under the camera I have my iPhone and then a machined housing, which I bought on eBay. And if I look more closely at the housing, by zooming in here, you can just get a sense of the machining process, the fact that different tools were used and different tool paths to achieve the different geometries. This is made out of aluminum and has quite complex features, as we'll discuss more later. And also as a finished part, after the many machining steps, there are other processes needed to make it. There's insertion of these threaded inserts, and there's what's called overmolding or insert molding of these plastic areas. But this is a really complex machined part, and Apple's mastery of CNC machining has been critical to its integration of design and manufacturing and the realization of a lot of its products. Here's a segment of a video that was published by Apple. You can find the longer video on YouTube, and this shows some steps in manufacturing of their MacBook housing. They call it the unibody because it's a single piece that holds a lot of the computer. Here we see the raw material coming in as cylindrical billets of aluminum, processing of the aluminum into flat plates, and then the plates are cut into rectangular pieces that are then machined to create the geometry of the housing. Now this video is only showing a few of the steps, the CNC milling here to cut the holes for the keys for the keyboard. Here's an operator moving the part to the next station and also blowing away some of the debris. This machine is actually laser machining, meaning it's using a laser beam to cut the little holes that allow the sound to come out from the speakers. And here's a finishing operation, finishing the side of the part. And when it's all done, the geometry is quite intricate. Now, Apple certainly had to invest a lot of time and money to master the machining process, but if you can create a market demand and sell such a large number of components, then it's arguably worthwhile. And also you could say that their mastery of machining influences their ability to design, and that's really important. Apple's continuing to grow their understanding of machining and their use of machining in their products. Here's a picture of one of their latest laptops, the 12-inch MacBook, which is really light and thin. You can find more on their website as well, and they show this exploded view of the design where they mention that they've machined out more volume from the inside of the case, so they can then make the battery larger, and therefore the computer can last longer without having to be plugged in. So what exactly is machining? We're familiar already with turning and milling as the two most common machining processes. And if you open up our favorite textbook by Kalpakjian and Schmid, you can read they define machining as a general term describing a group of processes that consist of the removal of material and modification of the surfaces of a workpiece. Now, what does that really tell us? Not much. It's a really general definition, but it does say that machining is removal of material and modification of surfaces, which we can't argue with. Now, we're going to talk most about traditional machining, where a rotating cutter containing teeth, one or more teeth, removes material locally from a part. And that's what you see in the diagrams of milling and turning, though obviously in milling, typically the cutter is rotating and the part is stationary. And in turning, the part is rotating and the cutter is stationary. But to an approximation, the mechanics are the same. Now, you might be aware there are other kinds of machining processes that use basically different physics to achieve material removal. And those include laser machining, water jet machining, and electron discharge machining, which uses an electric field to take material away. We won't really talk about those, but you might study those more in the future. So as I said before, machining is used to make a lot of things, and really things from small to large. A lot of machining is used to make the mechanical parts inside mechanical watches. We saw a moment ago the iPhone housing, and here's actually a picture showing both the iPhone 5 and iPhone 6 housings. And there are changes in the geometry and size of the housing, and of course changes in the machining process that was used. A lot of fittings, i.e. parts that are used to transport fluid, are made by machining. And also large components of aircraft are made by machining. I took the picture on the right at a manufacturing show that I went to about a year ago, and this is a piece of the wing of the Boeing 777, a very large commercial aircraft. And I stood next to that part, and it's about as tall as me, which is almost 2 meters tall. And you can imagine for the aerospace industry, machining lightweight, strong materials is really important. And also, a plane will use less fuel if it can be lighter weight. So optimization of the machining process so you can achieve that combination of low weight and high strength and high stiffness is very important. So there are many companies that make machine tools and innovate in understanding of the machining process, particularly so they can work with the aerospace companies. And also, when you think about geometries, it's already clear that you can machine a lot of different geometries, but in general, machining is good at making flat and curved surfaces, or the simplest processes of machining make flat and curved surfaces. So these brass fittings might have an engineering drawing that looks like so. This is not a drawing of one of these parts, but it's a similar geometry. And generally, the tolerances of machining processes, the roughness, the accuracy that can be achieved are roughly 1/1000th of an inch. And 1/1000th of an inch is about 25 microns, 25 micrometers. So if you were to make a dimensioned engineering drawing for a machined part, it might look like this. And machining can also create features such as threads. And I took a threaded part, such as one of these brass fittings, to an electron microscope, which can just show really, really fine details, and took a picture of the surfaces of the threads over here. The scale that's marked is 0.5 millimeter or 500 microns, and here you just get another sense with a bit clearer view of the texture of the fact that the material was removed in a turning operation. And if I look at the iPhone housing more closely, you can also see, of course, the machining marks left by the rotating milling cutter and the fact that the tool path was going back and forth like so in this area of the part. Here's the agenda for the machining module. First, we'll discuss the interaction between the tool and the material. Then we'll address cutting mechanics in 3 parts. First, we'll address the geometry and motion of the tool. Second, we'll discuss how cutting forces scale with process parameters. And third, we'll understand what determines the energy and power needed for machining. Mixed in with the above, we'll do a couple of demonstration experiments where we'll use a lathe and we'll apply different process parameters and, for example, measure the cutting forces and look at the effect of different tools on surface finish and tool wear. And while most of the above will be about turning, then we'll talk more specifically about milling, and we'll look in more detail at the iPhone housing and how it is milled. And then we'll discuss rules for design for machining, and we'll conclude.